Actually, I've been working with oil droplet on Tetrahymena, which is the kind of protozoa, right? And then from the temporal behavior of Tetrahymena and oil droplet, how I can differentiate between living and non-living systems, right? Because the Tetrahymena is believed to be a living system, right? Because they have the DNA, RNA, and then the behavior. But the oil droplet is apparently it's not living, I suppose. So first of all, in the first section, I'm comparing between Tetrahymena and oil droplet. And then this time, the oil droplet is not the one that I did in 10 years ago. This one is a mixture of, ES and also paraffin. And then put in SDS solution. But Tetrahymena is something that we got from, so we know completely what the DNA is and RNA is. So it's very much, so in a later that I'm going to show you how this sequence of RNA is diversification by interacting with each other. That's kind of thing that I'm going to discuss. So basically what I'm saying is that standard time series from the dynamical systems point of view is that we measure the atomic exponent and the embedded dimension, and then also nonlinearity, right? And oil droplet tend to be low dimensional, and then it's a low dimensional chaos. And also the embedded dimension is about 5. But Tetrahymena is something is high dimensional. It's more than 7 dimensional, but the instability is very, very weak with respect to the diagonal exponent. It's around 0.01 something. However, embedded, so therefore, I must, and then also nonlinearity is quite weak comparing with oil droplet. The oil droplet is much more, strong than Tetrahymena. So in summary, I think Tetrahymena is more noisy behavior comparing with oil droplet. Oil droplet is more like a deterministic chaos. So that's a difference. So I didn't know that. I thought, oil droplet is more stochastic and then Tetrahymena is more deterministic chaos, but it's the analysis shows different, right? So I was wondering why Tetrahymena is so noisy and so different. Then I looked into assembly of Tetrahymena. Okay. Then the thing can I use this one?
Yes, of course.
So usually, so this is something that the time series from n to n plus 1, and how in this time I computed the kinetic energy and how it changes over time. Right? Then I computed mutual information between xn plus 1 and xn. Right? But at the same time, I computed conditional mutual information, which is because this one is within an assembly, right? So I'm looking at the ith individual, and then this one is not I. Okay. So this is conditional mutual information. So if this individual I is highly affected by the other individual, then this goes to 0, right? But this is not. So if I compare with this one, and this one, and if this is larger than this, this is what we say. This is more autonomous. Autonomous organization, but if this one is larger than this, then we say this is more colonial organization. So, individual is not the free will of the individual is not just a random behavior, right? This is more driven by the other members of the behavior. Like Dan Dennett said, the free will is not the character of its own individual, but is given by the assembly or society, right? So downward causation provides free will to the components of the society. That's one of the things that I found here, right? So when I look into
This,
finally,
you can go.
so finally, what I got is
You can move it through.
okay. But how much can I use it here?
This,
Okay. Yeah, but that's what I wanted to say. Anyway,
maybe start the live show.
yeah, that's a good idea. So can I start? What?
Yeah, but for some reason it's not showing there. Yeah, so let's start the video.
Yeah. Anyway, so you can start. Well, okay. Well, so this is the Tetrahymena, right? I don't know whether you can say this is the living or non-living, right? But then next one. Yeah, so I'm just we are using a stereo microscope. Under the stereo microscope, the Tetrahymena is moving around, so that we are using a deep neural network to track everything, right, for about 3 hours. Then, yeah, we can skip to the next one. Yeah, so time series is like this, right? Then can go to the next one. Yes. Yeah, next one, please. So this is the droplet that I working with, for example. The red one and the transparent one. Also, that one is the size is sometimes different, and then also the initial configuration is different. What do I mean by different initial configuration? I make a droplet in this way or this way, right? And if you make a very flat one, then the flat one becomes more chaotic, as you see. Like the movement is very chaotic in a way that it is more lifelike, I might say. But the other one is more periodic. So people tend to say that if the periodic motion you can see, then you will say that this is not the living systems. But if it's more random and chaotic, then people tend to say it's a living system. So the first purpose is how to distinguish between chaos and randomness and also periodic behavior. Yeah, so this is, yeah, so, well, the one that I was working with Martin Hanzik, more than 10 years ago was putting anhydride with a high pH water. Then there is a convection flow inside so that they can move. You know, there's a two forces. It's a Marconian effect, and then also tension between this membrane things that the other guy was talking about. But now that I'm using this paraffin with ethyl 38, and then this one is more. I'm not sure whether there's an internal flow structure exists or not, but certainly there's environmental flow structures, so that it can interact with each other maybe. So the first one is the diaphragm spectrum. The diaphragm spectrum is once you have like 10 degrees of freedom, then we have a 10 different diaphragm exponents. If it's a Hamiltonian system, means that the energy is conserved, then we have a symmetric diaphragm exponent that we can say here. So, so this one is the diaphragm exponent. The maximum one is this blue one, and then lowest one is these violet ones. But the diaphragm exponent is around 0.15 to 0.03. That's the what oil droplet is. But for the diaphragm exponents of tetrahymena is 0.05. So it's a 1/10 smaller than the oil droplet. And also we computed the embedded dimension. Embedded dimension is what is the effective degrees of freedom for those systems described. And the effective degrees of freedom is, well, so roughly that we can compute Kaplan-York dimension, and then it's about 474. And Tetrahymena is 6. So this one is 6, and this one is 4.7. So Tetrahymena is more high dimensional. Yeah. Then, well, this is the what we call ESMA, and then, yeah, compared with, so whether there's a nonlinearity, it is strongly affecting the behavior or not, is you can measure by taking an ESMA analysis, which is this curve. So, in short, Tetrahymena is less nonlinear than oil droplet, and means that Tetrahymena is more high dimensional, and then, but it's noisy, and there's no, it's less deterministic. So that we try to understand this by using a Langevin equation. That's what usually at a very first step that the physicists try to use. And then this Langevin equation is the noise term, which is a symbol with xi. And then the first part is more like the torque forces. And then if you have more, if you say, then you have a chaotic. And if you have a more stronger driving force, and you have more chaotic and regulated behaviors. So Tetrahymena is in this region, and then oil droplet is in this region. So it's clearly separated that it's not easy to see from the time series, but if you use this model, that you can understand how this oil droplet and Tetrahymena is differentiated, like this one. We can skip this. Yeah. Okay. So it's, as I said, this is F is like a driving force, and D is a diffusion part. So Tetrahymena is in the region of weak force, but it's very much diffusive. It's more like the behavior is more like a random behavior, random walk. But the oil droplet is more strong force with weaker. Well, sometimes weaker, then you have a cyclic behavior. But if it's diffusion term is getting higher, then you have a helical or chaotic behaviors. So the point is that chaotic is for oil droplet, but Tetrahymena is less chaotic and something it's more stochastic, or you can say indeterministic. Let's skip this. Yeah, let's skip. But the interesting point that as of course, oil droplet cannot replicate many times for this system, but Tetrahymena can replicate, right? Well, the first one, this is the time series looking at the X coordinate, and this one, the second one, and fourth one, and third one, and fourth generation. Then, when I was looking into the kinetic energy distribution of each individual, so the first generation, and second generation, and third generation, and fourth generation, it looks like the shape is similar, right? So the shape of the kinetic energy is inherited to the offspring. That I was really surprised. I mean, so this is the different case, not other case. This is the first generation, second, third, fourth. So it's similar, right? So I think there are some inheritance mechanisms of kinetic energy distribution of this shape. But I don't know why this can be the phenotype or not. So we don't know what's the phenotype of Tetrahymena, but maybe this is one of the examples of sort of classic phenotype. So I computed the Kalbach library distribution, which is known as if you have two different distributions, and in order to measure the distance between this distribution and the other distribution, you can use this one, this carbon fiber or symmetrized Jensen channel divergence at a distance of two different distributions. If it's 0, it's completely overlap. And if it's 0.633, and then it is separated. Yeah, this one. So I compared 7 cases, starting from a different, different 7 individuals, and then we can have like a first generation, second generation, third generation, fourth generation. Then I computed the carbon fiber distance between two, time series. Okay. Then, as you can see, there's a 2 big block of the blue one. So these were two series that exist, right? But of diagonal, blocks, you have like more light blue. Means these 2 blocks, the one of the ABC and DFG has a different series, different sort of phenotypes. I think it's a big difference. And then, but within this phenotype also there are some small differences. So it's more like like a biological, what do you call it? The tree, inheritance tree that, even though those Tetrahymena has a completely same DNA, however, once they are replicating and interacting with each other, then they go to a different families. So I think, well, it has been known for other animals, like even E. coli has a speciation, right? So that people think that prokaryote never can, be different from multicellular system. But I think prokaryote is already potentially can be a multicellular system, I think. So I looked into sequential single cell RNA sequences by picking up 5,000 individuals, right? Then after taking the cell phase differences, cell phase is like MG1, M2. So there are phases in the cell, right? But even if there's a differences irrespective of cell phases. So on this side, there's also 5 to 6 different clusters like this. Means that even DNA is the same, but the phenotype can be different. So it's not only the kinetic energy that you can see the differences, but even if you go to see the gene expressions, and then there's the differences. So I think there is some sort of interaction noise that affects the behavior of each individual. Yeah, so this one is well, but I just use a different measure to see whether there are series or not. So then I calculate information closure. Okay, so information closure is maybe we'll go to the next one. So mutual information between Sn to the Sn+1, N is a time series, time index, and I is the index for the individuals. And then the second one is it's a conditional mutual information, as I said. Suppose you have the time series of the other individuals and how the mutual information between SNI and SNI+1. So this is very tricky. I can discuss this because this is very interesting. But if the colonial individuality, if the second term is larger than the first one, then we say this is a colonial individual. So individuality is determined by the society itself. But if the first one is larger than the second one, then we say, well, each one is more individually, moving around. So in this case, so I said there's 2 different big time series, big processes. Then the first one is until 4th generation, organizable individuality is less than colonial individuality. So until 4th generation, it's more, colonial individuality is dominant. But this one is more like it's almost same. There's no big difference. So I think it's it's more individual behavior is determined by the colonial in the the first three cases. So the upper left corner, this family is more a colonial individuality is dominant comparing with the organizable individuality. So, well, the takeaway is that the low-dimensional chaos is what all the droplets show, and high-dimensional, less nonlinear, but the rather stochastic behavior is what Tetrahymena shows us. Right? But in short, Tetrahymena behavior is more noisy. But the question is where this noise is coming from, right? It's very noisy, but the almost condition is the same. But why this is more noisy than comparing with the oil droplet? So I say that noise is coming from community, which an individual is belonging to, and the noise can be interpreted as a free will. So I know that's going to be very much argumentable, but I think noise coming from the community is what we see is the free will. That then at this point, I agree with Dan Dennett that free will is nothing to do with the deterministic or stochastic, but it's more about how you can interpret in that society. Thank you very much.